Hi, I'm Borno, your organic chemistry tutor, and I'm back with another mechanism problem that we're going to work through together. Let's get started on it. Alright, so this is the mechanism problem that I have for you today. You should be able to do this problem if you have learned electrophilic addition to alkenes. So if you have, I suggest that you pause the video, try this mechanism on your own, and then come back. Alright, let's see what is going on here. First of all, it appears that my alkene has had basically an S-phenyl and an iodine added to it on different carbons. So that seems to be a typical addition reaction to an alkene, but really, what is the mechanism of this transformation? Like, how does this happen? We've never seen something like this before. Now, let me remind you of something. In the bromination mechanism, what we think is happening is that as the bromine molecule approaches the alkene, the electron cloud of the bromine molecule gets distorted, so one end of that bromine molecule becomes positive, one end of that bromine molecule becomes negative, and that is the reason why it does basically get attracted to our alkene, which is full of electrons, and form a bromonium ion, and that bromonium ion basically is at the core of this bromination mechanism. Now, this is kind of a similar thing. Let me tell you why. We have an S-iodine bond, and that S-iodine bond is highly polarized towards iodine, right? Because iodine is more electronegative than sulfur is. So this is like bromine, except at all times it is polarized. So when that approaches the double bond, it can form something basically pretty similar to a bromonium, except with sulfur. And that is going to look something like this, basically. So I have a methyl here, I have my sulfur atom right here, I have phenyl, and this thing is charged. And whenever we have something like this, a three-membered ring that is charged, when the nucleophile, which is iodine in this case, or I minus rather, iodide in this case, when that comes in, that is going to attack the more substituted side of that double bond, or rather, more substituted carbon of that three-membered ring, because the more substituted side of the three-membered ring is going to have more positive charge on it, because it resembles the more stable carbocation. And it turns out that these kind of reactions are basically controlled by charge. So the iodide is going to go for the position that has the most charge concentration. And also it is noteworthy that this intermediate is basically formed in a racemic fashion, meaning that the three-membered ring could form from either face of the molecule, and that means that at the end of the day, the product that I'm going to get is also going to be racemic, and iodide is going to be on the opposite side as the S-phenyl. Well, if you like this video, please don't forget to hit the like button. That's going to help my channel grow. Also, share this video with your friends. Subscribe to my channel to see more tips and tricks, solve problems and tutorials, and I'll see you in the next video. Take care.